Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 54 today and we are discussing about ways to enhance adhesion of an adhesive without invoking viscoelastic effects. So, we presented one mechanism that is called crack arrest and initiation on a patterned adhesive, and in essence we have this adhesive in which we have this adherent. Adherent is lifted off this particular adhesive from this edge of this particular adhesive over here, and we also introduced cuts along this path of this surface on this adhesive, and this cuts and incisions that acted as a split breaker for this adhesive, for this crack. The crack arrested and crack initiation happened and the adhesion strength kind of increased. So, in essence we can plot or we can obtain this fracture energy with respect to the height of this incision, depth of incisions. So, for example, by depth I mean that this is the adhesive, let us say, and then this incision is up to which height. So, that is at height, let us say h. So, it can be incision can be up to this height, can be this height, can be this height. So, in the earlier experiment I had the incisions which were whole through the thickness of this adhesive, whole through the thickness of the film, but now we have varied this incision thickness height, and that leads to different fracture energy. So, here also one can see that the enhancement in adhesion, this is about 10 times over the smooth film. So, this was about crack arrest and initiation mechanism, and why we are excited about this is because that in nature many animals at the feet they have this adhesive pad by which they can stick to different surfaces, and they have to do it reversibly because they do not only need strong adhesion to an surface, but also easy release, and they have to adhere once again. So, the ability to adhere to surfaces of different types and reversibly, adhesion force 50 to 100 times their body weight, because they can this bush cricket or the frog and the lizard, lizard, this is a lizard feet, they are able to do that and they need to do that. So, strong adhesion yet easy release. So, that they have to satisfy, and it seems the surface of the adhesive pad is not smooth, they have got this kind of incisions or cuts or structures. So, for example, here this looks like perfect hexagonal structure, then there are pentagonal structures over here, and if you magnify this surface you will possibly get even finer structure, and it seems they have also got this kind of fluidic glands through which the fluid comes out in so many cases, not for all, but all some cases like frog for example, and many cases this helps them in weight adhesion and so on. So, in nature there are a variety of physical mechanisms which are used for enhancing adhesion, and these are all physical mechanisms, not chemical, because chemistry remains same. It is just that the surface of the adhesive is patterned or structured, the structures below the adhesive pads also have got patterns and like that. So, we have it is worth investigating or looking at that how these structures help them in enhancing adhesion. So, that is what we are actually discussing about. So, crack arrest and initiation, contact length splitting, these are the mechanisms that definitely play a role that we have seen earlier. So, today I would like to discuss another topic, another similar topic, it is called crack arrest initiation, but on a virtually patterned adhesive. What I mean by this is the adhesive is smooth from the surface, but there are patterns and structures underneath the surface, below the surface, and therefore, these are like virtually patterned adhesives. And in fact, so what we are going to show you is that the adhesive itself may be smooth, but there may be patterns, structures at the adhesive surface, adhesive at the bulk, that can also enhance adhesion. So, basically what I am going to talk about is this. Here we have this adhesive film which actually bonded to a rigid substrate, but look at this adhesive film is not completely continuous. We have embedded some fine channels or fluidic vessels inside this film. So, I will like to show you this in an experiment, that how do you do this experiment, okay, and how these films look like. So, let me show you this adhesive film, so which is actually bonded to this glass plate over here, this glass plate over here, and then it has got, you can see from here there are these lines you can see. So, these are basically these channels which are embedded inside. So, these channels, as its figure shows, is on the bottom surface, it remains on the bottom surface, and this is the film everywhere. So, there is a thin layer of the film that remains on the top. So, from the top the film is actually smooth. So, if I use this Scotch tape, okay, it will completely come out, in contact with the surface. There is no problem there. So, it will surface. So, you can see that it has completely come in contact. So, from the surface it is smooth, but then you can peel it gently also, okay, no issues. So, from the surface it is smooth, but it is not smooth at the bulk of it, because at the bulk it has got this kind of micro channels inside. So, here this film is brought in contact, this copper flexible plate is brought in contact with this film over here, and then you lift it. So, then what happens? So, in this case this is a virtually patterned adhesive, in the sense that there is no pattern on the surface, but pattern is at the inside the bulk of this particular adhesive. So, adhesive layer embedded fine micro channels, and flexible plate is brought in intimate contact and then lifted. So, this is a video I would like to show you that from this experiment. So, when you lift this flexible plate, then this crack appears at the surface, but then this crack gets arrested at the vicinity of this micro channel. So, the channel is at the bulk, channel is not on the surface, but the crack does get arrested at the vicinity of this channel, and then it once again opens at the other side of the channel, very similar to the crack arrest initiation or the incisions that we saw in the last class and last few lectures. Again this gets arrested. So, the crack gets arrested at the vicinity of the channel, and then it opens up, and then propagates quite relatively faster, and then once again gets arrested. So, this way the crack arrest and initiation that happens on these virtual cuts as well. So, here if you look at distance of the crack line or the contact line from the spacer or edge of application of the load, that is A, and that goes with respect to time. So, it moves for certain time, but then remains at rest for a long time, this is called crack arrest, and then crack propagation. So, the crack propagation happens only this much time, crack arrest happens on this much time, something like that. And if you look at the torque, then the torque also goes this kind of oscillations at this particular peak corresponds to the crack initiation from the edge of this particular film, and then the crack gets arrested and propagates once again from the other side of that channel, other side where the channel lies, and so there as a result this torque also shows this kind of oscillatory behavior. So, this is for a smooth film, and this is for this films having this kind of channels. So, you can see that because of the presence of this microstructure or virtual cut, okay, this crack initiation, okay, at the vicinity of the channel leads to enhancement of the adhesion. One can further characterize it with respect to different parameters. So, one of the parameter here is the film thickness. So, what it means is that you have got, let us say this is the channel actually lies on the way the channel is made is lies on this bottom surface of the glass plate over. This is a rigid substrate on which the film remains bonded, and this is the film. So, this film thickness is varied. So, this is H, and let us say this is D. So, the D remains constant and H is varied. So, as H is varied, the skin thickness that varies. Okay. So, with increasing H, that the skin thickness that increases. So, that is what happens. So, that means when the H is minimum, the skin thickness is also minimum. So, that corresponds to this data. As the H is increased, then the skin thickness increases and then it decreases. Skin thickness increases continuously. So, skin thickness is continuously increasing, okay, from left to right over here. The diameter of the channel that remains constant, and the channel is over here on the surface of the substrate. So, what we see is that initially to some optimized thickness the torque that needs to be applied, average torque. So, average torque means that you find that a torque that is average. So, torque slightly decreases, but all or more or less average, let us say this average torque that increases and then decreases. So, the increasing part we say that this is the effect of the skin thickness. As the skin thickness increases, there is a compliance of the film that increases. Okay. So, if it is compliance means that this part of the film that remains to that wants to remain in contact with this particular top surface. Okay. Basically the top surface, the flexible plate is being lifted off, and so the crack propagates, but the film by compliance the kind of tries to remain in contact with this flexible plate. So, that is compliance, and at the skin thickness further increases, then the effect of the channel decreases, because channel is goes further and further down. Okay. So, this skin thickness is much larger. So, then the effect of the channel goes. So, therefore, there is a non-monotonic behavior here within certain range of thickness the effect increases and then decreases, which is expected. So, how exactly this embedded channels that work? So, it is shown here. So, here this is the schematic elastic film, this is the skin thickness over here, as I was telling you this is the skin and so on. Now, what happens that when you have got the incisions, then instead of channel you have got complete cuts like that, and you have seen that when we analyze this problem for the under lubrication approximation, okay, the del P by del Z in the film is constant. So, the skin thickness within the skin also the pressure is actually constant. So, the pressure may vary spatially with respect to distance, but with respect to thickness, okay, in the film it is constant, that is what it means. So, as a result you can see that here the pressure is 0 atmospheric, here also this is atmospheric because pressure is 0. So, as a result pressure is 0 here, pressure is 0 here, within the film also pressure is 0 therefore, and so as a result del P by del Z becoming 0, the pressure inside this film, the skin thickness within the skin is also 0. So, which is very same as over here where there is a pressure 0 everywhere. So, as a result this micro channel over here that kinds of acts as a virtual cut, okay, as a virtual cut. It is not a complete cut, but it is a virtual cut or virtual incision, and therefore, okay, this it does not matter. So, basically that is the idea that we say that this is a virtually patterned surface which leads to this particular effect. And also we have seen that the peeling torque is independent of the vertical location of the channel. So, we have done experiments in which let us say in this case the channel is lies on this particular rigid substrate, but let us say channel remains somewhere here, then also the peeling torque, okay, does not matter, because it is because of the same reason that this is a virtual cut over here, okay, like this. And we can also estimate the energy dissipation by the area under the curve calculation. So, the force versus displacement, and then you see the force displacement, force goes like this, and then we can calculate the total energy which is spent, okay. And so, how do we characterize that? So, we can actually from the torque also we can actually estimate what is the enhancement in the energy. So, the fracture energy given is given by m square by 2d. So, that comes from the mechanics of the thin sheet thin plate. So, we can actually obtain that m square by 2d is the energy that is because here the energy is mostly in the bending energy, okay, that is why bending energy of the plate. So, that is why fracture energy is like that, and the volume fraction of the channel that can be obtained. Okay. Volume fraction of the channel means within the characteristic length scale with the characteristic dimension length scale, the volume of the channel is like this. So, from there, from this analysis and all that, okay, one can get this quantity called the void fraction, that is alpha, and from that one can get that what is the remember that here this quantity comes because this h into k inverse the total area, total volume, let us say h into a volume means volume per unit width of course, and this pi d square by 4 is this particular volume of this particular channel. So, this is all every case that is multiplied by w here, w is cancelled. So, this is the void fraction, and so now you see that from data from all different experiments, okay, that fall on a single master curve like that. Okay. So, that is the analysis part of this experiment, and one can do it of course much more rigorous further do these things. So, how exactly this crack arrest initiation works? So, let me tell a little bit about that. So, here you see a gecko's feet shown here. So, the surface of the feet or its fingers, it is not smooth structure, it is a lamellar structure like that, okay, very similar to the crack those incisions that I made on those films. And over here what happens, something like this. You have this top the flexible plate, and when you try to open the crack, this flexible plate stretches this amount of the film. So, there is some amount of elastic energy that gets stored, and as the film, this particular plate is lifted further, this contact line that moves. So, if the contact line moves, this portion of this film that goes down, but this portion of the film now has to get stretched. So, the stretched portion that also propagates. So, the stretched portion stores some amount of elastic energy. So, this elastic energy, okay, that gets propagated, okay, continuously from the left side to the from the right side to the left side over here, because the adhesive film is continuous. So, this elastic energy that is stored, that can propagate, okay, propagate nicely, uniformly, continuously. So, again to repeat, as when you lift this plate over here, this film has to get stretched, okay, this is a magnified view of course, and it stores some amount of elastic energy, and as that film is, this cover plate is lifted further. So, this stretched portion that has to move, and that moves from here to here. So, as this portion moves to here, and this portion, this stretched portion that goes down over here, okay. So, as a result, there is an elastic energy part, energy front that propagates, and that can get propagated continuously because the film is smooth. Now, over here what happens? As the film is, the plate was initially over here, this part of the film got stretched, but as this crack propagates from here to here, crack propagates here, the elastic energy that cannot get transferred, because there is discontinuity over here. As a result, this portion which got initially stretched has to relax, and when it relaxes, okay, it relaxes under zero load. So, under zero load relax. So, as a result, this energy, elastic energy, that is actually get dissipated, okay. So, this energy, elastic energy cannot get transferred over here. So, as a result, this energy gets dissipated, and this portion, in order the crack has to propagate, this portion once again has to get stretched, okay, like that. So, it is the elastic energy dissipation, okay, that happens continuously on when you have patterns like that, and that is why this energy spent in opening this in debonding this flexible adherent from this adhesive, that increases. So, that basically is the physical mechanism over here, that the elastic energy front that cannot propagate continuously, that energy that remains localized, it has to get dissipated over here, and then the next portion of the crack, next portion of the film has to get store elastic energy once again, develop this elastic energy once again, okay. So, this you need to, so external load has to do more work in order to propagate this particular crack or remove this drive this flexible plate, and like that. I will now describe another mechanism of enhancement of adhesion, okay, which is known as self adhesion hysteresis. So, we are discussing about that how we can enhance the adhesion strength of an adhesive without incorporating viscoelasticity. So, crack arrest and crack initiation one mechanism, the contact area splitting is another mechanism that we have discussed. We also discussed about virtual cuts or virtual patterns. Now, we discuss what is known as the self adhesion hysteresis. So, basically here there is the idea is the dissipation of energy following intimate contact and then separation of two identical surfaces. So, self adhesion, because the material is adhering self on it, okay, and those mechanisms of energy dissipation that happens by this different ways. Hydrogen bonding interaction between surfaces. So, let us say one surface is there, another surface is there, and initially there was no hydrogen bonding, but as you are giving it more time and applying more load, let us say, okay, these surfaces come in intimate, more and more intimate contact, and they have got these wedge groups and groups which can form hydrogen bond, and they lead to formation of this hydrogen bond across this. As a result, when you now try to separate it, there is a hysteresis that happens. In the absence of this hydrogen bonding, there would not have been a hysteresis. So, that is one mechanism. Then adhesion of rough surfaces interface at non-equilibrium metastable state. I will describe it, but what it means is that suppose you have got a rough surface like that, and as you apply load, they want to come in contact, intimate contact, and because of the adhesion and because of the softness of that substrate, they continuously come in contact. There is no equilibrium that is reached. The surface or interface is at a metastable state. Okay. So, there is a kind of aging phenomena that goes on. So, as a result, there is this hysteresis that happens at the interface. So, if you give more and more time, okay, this surface will come more and more in contact, or if you apply more pressure, they will be more and more in contact. So, this phenomenon, this situation is very different from a completely smooth adhesive, in which case there is no such metastable state or non-equilibrium state situation. The surface comes in equilibrium and the work of adhesion we find out from the surface energy and like that. Then of course, there may be other surface viscoelasticity, the effect of humidity, temperature, okay, all these things affect this basically this phenomena. So, we will like to describe few of those methods that we can implement in the adhesive layer. So, again here hydrogen bonding I have said here given. So, let us say the surface has got hydrolyzed. So, initially there was CH3 bonds, let us say hydrolysis occurs. So, you have got now H2 groups, say here CH2H, another surface, okay, having CH2H groups. These two surfaces they come in contact, and so as a result there is hydrogen bonding, and that will lead to this formation of hysteresis. So, this particular paper you can see where this hydrogen bonding or this OH groups are introduced by hydrolyzation of the silicon surface using dilute HCl solution. So, this mechanism I am not going through, but this is the hierarchical rupture adherent. So, as I was telling you that dynamically altering interface, aging effect, addition of soft and rough surfaces and like that. In this particular case, remember that of course, you need to apply certain amount of load to bring them together, but because of the deformability and adhesion between them, okay, the contact gradually increases, and as a result there is a dynamic situation that arises over here. Okay. So, this is also a mechanism by which hysteresis can happen. Hydrogen bonding in presence of moisture can also happen, because OH groups, H2O has got this OH and it can form bonds and like that, that can also lead to this kind of phenomena, and this hydrogen bonding or the presence of moisture that can affect when that can play a role when you have this kind of rough surfaces, because water can actually go and form a meniscus, okay, at this between these asperities. So, the surface has got this asperities and there is a large curvature there. So, the moisture can go and condense over here, okay, by Kelvin effect. So, there are quite many complicated situations may arise, okay, which deserves attention. So, here I will present few experiments that we did in order to explore this possibility or exploit this as self-adhesion hysteresis in order to enhance adhesion. So, in essence here we have this adhesive layer, and I saw the microchannel, circular microchannel, but here the channels is rectangular cross section, and these channels can be in single layer or multiple layers or like that. So, the surface of this adhesive is smooth. So, this is smooth, no issues. So, this is smooth, but then on the bulk it has got this kind of microchannels. These microchannels can be made by different ways, and here is for example, there are some templates that has been used, basically thin sheets which has been placed inside, the adhesive has been made, and there is a way to take out these thin sheets. So, basically template assisted methods, and this can be seen in this particular paper of my student Peter Arul, and then you do this experiment has been done by bringing an indenter, okay, in contact, and you press it and then lift it, and as a result what happens that you have got, let us say, this adhesive, and then you have, let us say, this particular channel, this is another channel, this is another channel, this is another channel, like that. Now, you apply the load over here, because of this there is deformation like this. So, deformation, so this channel also deforms, finally these two surfaces come in contact. So, they bond over here, okay. They here also they come in contact, they bond like that, and now depending on the load, and now there is self-adhesion hysteresis at each of these interfaces over here, self-adhesion hysteresis. As a result, when you now lift it, then the load, these surfaces do not come out of contact instantly, okay. There is you need to apply some amount of pulling load in order to bring them out of contact, and that leads to this enhancement in the adhesion. So, here this the cross sectional picture of this particular adhesive, as I was telling you, it is a very thin gap between them, but that is enough for this effect, okay, to work. and these channels can be of different size and shape. For example, here it is a curved channel, would have been there is a V shaped channel and blah blah. So, we can do many possibilities over here, and then this is one video I will play, and then I will stop for today. So, here this is being pressed from the top, this indenter is pressing, and we can see that these surfaces they came in contact, and now it is being lifted up, and you will see the this separation is not happening instant. Over it is happening nicely, but here it did not happen instantly, here also did not happen, here it happened after some time, or like that. And this has this effect on the force displacement plot. And so, here for example, like if it is a smooth case, so it will be this is the loading and this is the unloading, and this is P and delta are the P as a function of the force as a function of displacement, and as you unload it, this there is a little pull of load that needs to be applied, because there is a adhesion between this indenter and this particular surface. But over here there is a single channel, so the load increases. Now, you see that the slope is less because the modulus is less here. The effective modulus is less because there is a thin skin here, and then this thin skin and then 2 dash they contact over here. So, as a result, now the modulus increases now, because now it is same material, it increases now, further increase in load, it the modulus now increases. So, the displacement similar displacement will require now more load to apply. Now, let us see to the unload. So, when you do the unloading experiment, then it is not that this curve is followed smoothly, no, it actually decreases, and when it gets separated, then so there is a pulling happens separated, and once again this happens it comes out and like that. So, if you see in a way in this region there is a kind of negative modulus that happens. So, it is a kind of metamaterial effect that comes into the picture, negative modulus over here, and then again it has the slope gives and so that is the effect that we take advantage of, and that leads to enhancement in adhesion. For example, if it is a solid material, then we will have this much amount of adhesion. On the other hand, if you have one with single channel, just single channel, and from this with the difference between these two area under these two curves, loading and unloading, this leads to this much amount of adhesion, this much amount of energy. So, you can see that here the energy dissipation in this particular case, this is self adhesion hysteresis is quite large, that is what happens. So, it is quite significant. So, this effect can be made use of and can be used not only for single layer of channel, but actually for multiple layer of channels, and each case there is this negative negative modulus that I am saying, that effect that goes on. So, this metamaterial effect is helps out here, and we can enhance the adhesion over here, because we can now see this cumulative hysteresis goes to as high as 15 about 1600 millijoule per meter square, from 40 to about 300 to about 1600 millimeter square. So, that is the interesting aspect of this particular microchannel embedded in multiple layers of channel embedded in this adhesive film. So, today I will stop here, and I will continue this discussion little more in the next lecture. Thank you.